Okay, so announcements first. So there was an issue with Lab 2, right? I sent a Blackboard announcement out. I forget when that was. It was Thursday? Last Thursday? Okay, so yeah, so there's a slight issue with Lab 2. The second part of the 3 parts where it asks you to verify that the system does anti-aliasing filtering before it samples. So the issue is that the sound card just seems to like pretty severely sample everything above 22 kilohertz, regardless of whether you're sampling at a rate that requires that or not. Presumably because it's like audio hardware and people can't hear above that frequency anyway, so it just filters that no matter what. So that part of the lab didn't quite work. So I just modified it. If you just lower all the frequencies down to like below, like 10 kilohertz, then it all kind of works as planned. So I modified that. I reposted the change version. We moved the due date from last Friday to this Friday. Just so you can finish that one part. I'm sorry that was mixed up. I think we changed the ComCloud hardware in January 2017, and I think the old hardware didn't operate this way. The new hardware did, and somebody didn't catch that when we changed the hardware. It's a bit mysterious to me that we had a whole spring class that did this lab, and somehow neither the students nor the grader nor anyone flagged that there was something amiss with this. But so we didn't catch it until now, so I'm sorry about that. But anyway, at least we caught it. So that's what's going on with that. So. So an extra week just to do that part. Lab 2 was not that long to begin with, but extra time to do that one part. And then we have homework 3 now due Friday. It's the usual due date for, not for Lab 3, homework 3 due this Friday. And there's one extra problem for the 5670 students on homework 3, just as there was with homework 2. I posted 2 more chapters of the notes, chapters 3 and 4. It's modeling the channel and the LTI system theory stuff. So those chapters are up online. I owe you the next chapter on communication, which follows the modeling the channel chapter. So that's where we stand. Any questions? Are we good? Okay, so today we'll finish modeling the channel. We have just a little bit more of that left to do. I was hoping to finish it on Thursday. We didn't quite finish it, so we'll finish that, and then we can actually start talking about designing communication systems. Okay, how to do it. Okay, so let's finish modeling the channel. So we talked last week about like why you'd want a model for the channel, like why you need one, and why it's not a good idea to just like plunge in and start experimenting with stuff. So we need a math model for our channel, for the ComCloud channel, and we start with a block diagram. I'll run through this one last time right now. Okay, so we're designing an encoder and a decoder. The encoder accepts bits. It creates audio samples. Those audio samples we're going to play through the ComCloud system. So it passes through a bunch of blocks as such. It passes through a quantizer, which this is essentially like when you call audio write in MATLAB. You're saving your audio samples as a WAV file with reduced precision. Okay, and that's essentially the quantizer. We'll talk more about this block today. We haven't gotten to this block yet, but so you have the quantizer. And then it goes to the sound card. The sound card has a DAC in it, so it converts digital to analog, discrete time to continuous time. Headphone amplifier through the RLC filter, and actually brought one of the filters open, so you can see it. So maybe I'll hand it. First for the camera, okay, and then I'll just hand it around. There's not much to it. It's like it's 1 inductor and 2 capacitors, so it's mostly the jacks and stuff in there. But anyway, so that's the channel proper. Okay, what kind of models the physical channel that we'd be communicating over. Okay, the output of the filter is passed into more amplification of the receiver, and then you have a ADC, analog to digital converter. Quantize again, and you get audio samples. Okay, and we're designing the decoder that takes the audio samples and extracts the bits from it. Okay. All right. So I mentioned last time, since we're designing these 2 blocks, we're going to call everything outside these blocks the channel. So all of these things together comprise the channel. That's why we call this the channel proper, to distinguish that box, from this other stuff. Because if we're designing these 2 blocks, like what we care about is the end-to-end performance from here to here. How does this vector get transformed into this vector, right? And whether a particular impairment arises in the channel proper or in the amplifier or here, it doesn't really matter, okay? Because we're seeing kind of the composite behavior of the tandem of all these systems together. So we lump them all into one entity that we call the channel. And that's what we're trying to model, okay? Okay, so we modeled kind of inside out. So we started with just developing a model for the RLC filter. And then we discussed how to add amplification to that, and DAC and ADC. And when we paused here, we had a model from X2 to Y2. That's like the input model from the input of the DAC to the output of the ADC. Okay, and the formula we got for that was this. Okay, it was rather busy. Okay, so this is a system, if you will, that takes as input this discrete time signal that's an input to the DAC. It spits out as output the output of the ADC. Okay, and it's got a lot going on. Okay, so you have, this is the reconstruction pulse in the DAC. That's G. There's low-pass filtering for the anti-aliasing filter in the ADC. That's here. You have the impulse response of the channel proper and the two amplifiers together. That's H. Okay, you have the sampling frequency. Tau, this tau parameter, if you remember, captured the fact that even if the transmitter and receiver are sampling at the same rate, their samples are not perfectly aligned, right? They can be perfectly aligned or they can be kind of offset like that. And tau captures the offset, all right? And noise. And we talked about the sources of the noise, thermal noise, shot noise, etc. If you ignore the noise, okay, one of the problems in homework 3 is to show the map from this to this is linear time invariant. Okay, so just view this as a discrete time system, even though it's got like continuous time stuff going on under the hood. End to end, it's a discrete time signal, right? Or discrete time system. It maps one discrete time signal to another. Okay, so one of the problems in homework 3 is to verify that discrete time system is linear time invariant. Since it's linear time invariant, we know we can write it like this, right? Y2 is just x2 convolved with some impulse response, right? This impulse response has got a lot in it, right? It somehow encompasses all this stuff in here. It's got tau, it's got H2, it's got G, okay? But no matter. It's some impulse response that you convolve with x2 to get y2, okay? So the system from x2 to y2 collapses down to something relatively compact, namely this. We talked about the noise last time. It's we talked about why it's, I said a few words about why it's IAD Gaussian, and showing this will hopefully be a problem the 5670 students can do after they've covered power spectral densities and so on in 4110. Okay, but right now we'll just take it as a given. This noise, the discrete time noise here is IAD Gaussian. Okay, so there are a few remaining elements left to cover. So one is we haven't covered the quantizers yet. We got blocks left. There's clock skew and finite length truncation. Okay, so clock skew, I think we finished with this on Thursday. So I just pointed out that these two F's here represent different things in a sense. This F came about from the transmitter. This is the sampling frequency of the transmitter. This is the sampling frequency of the receiver. Okay, we're tacitly assuming here they're the same. If they are the same, then the system is linear time invariant. If they're different, then it's not. Okay, in practice, we know they're not exactly the same, right? How far are they apart? 1 part in 10 to the 5, right? It's a number I recommend you memorize for this semester. Okay, the clock skew is about 1 part in 10 to the 5. Okay, so they're not exactly the same in practice. If we incorporate that in the model and put F1 and F2 here, the system's not time invariant anymore, so we lose a lot. Okay, the whole LTI systems theory that we know and love, you know, out the window. Okay, so there's a big cost to incorporating that particular impairment in the model, so we're not going to do it. We're just going to assume the frequencies are the same. Then the model is LTI. And we just have to remember that like this model is valid only over time horizons on, you know, significantly shorter than 10 to the 5 samples. Okay, once you have more than like a couple seconds of samples, okay, then you're going to start to see the clock skew, and this model is not quite right anymore. Okay, so that's clock skew. I think we ended exactly there on Thursday. So any questions? Okay, so let's do quantization. This does not take very long. Okay, so quantization involves taking a range, in our case, say -1 to +1. So the amplitudes in wave files are always between -1 and +1, right? So you take that range, okay, and then you partition it into little regions like this, okay, and then designate a particular value for each region. Okay, and then you can define some function I'll call the quantizer. And gamma of x is just, you know, I'm going to write it in English here, the orange point closest to x. Okay, so you just sort of round, you know, to the, I mean, it's not literally a round, I guess you can think of it as rounding. It's like rounding to the nearest orange point. Okay, that's quantization. Okay, so on some level there's not a whole lot to quantization. You just round to the nearest point. On On another level, it's actually a very deep subject. Okay, so I have like friends at other universities. They teach entire semester-long classes just in this. Okay, which at first blush is sort of surprising. It's like, what can you say about this? I mean, you draw these points and you round, and you know, it's like a 5-minute topic, right? So just give you a sense of what you can do here. Like this, so this, they call this a uniform quantizer, as discussed in the lab, right? These orange points are kind of spread uniformly over the range. Zero's somewhere in here. But in practice, you might want to actually kind of have more concentrated points around 0. So you might want to kind of do something more like that. The idea being that like the signal is more likely to live around 0 than at these extremes. So maybe you want to put more points there. Or maybe you care more about the relative error rather than the absolute error. So when x is small in amplitude, you want kind of proportionally smaller quantization error. So there's that. So how do you want this? Do you want this? If you're doing this, how exactly do you what concentration of points do you put where, and so on. So there's that. The quantization is also related to lossy compression too, which is another reason there's so much to say about it. So I said a bit about lossy compression in the first lecture, if you remember. People can dial it back all the way back to August. But so lossy compression like AAC, MP3, JPEG, MPEG video, and so on some level, okay, they're just like dropping precision. So they're just quantizing. Okay. Turns out, like I said in the first lecture, turns out it works a lot better if you drop precision in like a frequency domain rather than a time domain. So rather than taking your music and just like dropping, the least significant byte for every sample, and then at the receiver just padding that out with zeros. Okay, you're better off taking like a DFT, like block by block, or take the DFT of the whole thing, okay, and just like drop the least significant bits across the whole frequency domain, and just save that as your compressed file, and then on the receive side, read it in, pad out zeros for all the missing bits, take the inverse DFT and play. Okay, that's like it's like AEC from like 30,000 feet. Okay. But then you can ask, well, why are you better off quantizing in the frequency domain versus the time domain, and so on? So this is where it gets kind of complicated. But we don't really need any of that. For us, this is just like a simple rounding procedure like that. And like I said, it arises 2 places. So easiest place to see it is in the receive sound card. So you got continuous voltages being measured on the RLC filter, right? And ultimately, it's being mapped to a wave file, like 16 bits per sample, 24 bits per sample, right? So clearly, you're losing precision when you're doing that. Something is rounding, right? These continuously modulated voltages to just, 2 to 16 points. What's happening there? It also happens here too, in that, like in MATLAB, you might, to construct your audio samples, using double precision floating point. When you save it as a wave file, though, it's got to go down to 16 bits per sample, or at most 24 bits per sample. So you're losing precision there too. That's also quantization. Okay. Quantization is a little bit hard to work in the model if you really want to be faithful to the process, because it's like intrinsically nonlinear. Okay, like this is like an intrinsically nonlinear thing. So like, you can't really hope to kind of work it into here in a way that preserves the linearity of it. So what we're going to do is fudge it. All right. So let me show you what I mean. So let's think about the receiver. So the decoder anyway. So the decoder is not really observing like Y2 directly. It's observing the quantized version of Y2, right? So it's not really, doesn't get access to this. It gets like gamma of this, right? It gets quantized Y2. So consider gamma of Y2n. So this is what the decoder is observing, right? And let me write this as Y2n plus gamma Y2n minus Y2n, right? I haven't done anything. Yeah? All right. This Y2, the first one, I'm going to expand in this form right here as a convolution plus noise. Okay, so this first Y2 we can write as x2 convolve with h, evaluate at sample n, plus I have noise, right? That's just from that board. And then I have this term left, right? Gamma Y2n minus Y2n, like that. Okay? You see the fudge I have in mind? What about now? In English, what's the fudge here? What's that? Throw it in the noise, right? The quantization error, okay, the information that's lost when you quantize, we're just going to like lump that in with the noise, okay, and just call it noise. And like on some level, this is not a fudge, right? I mean, this is literally true. I mean, so that's trivially true, right? Here I plugged in and I added parentheses, okay? So like this is not really a fudge up to this point, okay? You can certainly take the quantization error, lump it in with Z and call it all noise. Like that's completely harmless, okay? But where the fudge comes in is that we're going to continue to assume that this term here, okay, is still Gaussian and is still independent of the signal. So that's, I guess, one assumption I left out over here that maybe I should have re-emphasized from a past lecture is this Z is assumed to be independent of the X2 signal, okay? So we're going to continue to assume that this noise plus quantization error is Gaussian and independent of the signal, and that's where the fudge comes in. Okay, quantization error is not Gaussian distributed, right? You can tell just looking from this, right? It's going to tend to be more like a uniform distribution, right? It depends on the distribution of X, but it's going to tend to look more uniform-like, right? It's not going to have long tails. I mean, the error is kind of bounded by the distance between two of those orange dots, right? Moreover, the quantization error depends on X, right? I mean, if X happens to be an orange dot, quantization error is 0, right? Okay, so the quantization error is dependent on X and is not Gaussian, but we're going to lump it in here and just assume it's independent of X and Gaussian, okay? And let me try to convince you that this is not an unreasonable thing to do, even though it looks so inaccurate on the face of it. So let's just run some numbers. That's one thing I like about this class, actually. You prove theorems, then you also like run actual numbers through the theorems, through the calculations, and see what it tells you. So standard deviation of the noise, let me just recall. So Zn, zero mean Gaussian variance n. Okay, remind me, here's the other key number to have memorized. What's the standard deviation of the noise? Order of magnitude for our channel? Flippin'. I don't know if I've mentioned it in class, have I? But it was the first lab was just measure the noise level. No dice? Yeah, I mean, either you know it off the top of your head or you don't. It's hard to look up at this point. So it's order of magnitude, this is about 10 to the minus 5 volts. Okay, so there's like two numbers to memorize, and it's easy because they're both 10 to the 5. Okay, so the standard deviation, one's 10 to the 5, one's 10 to the minus 5. I guess they're both 10 to the minus 5, right? So the clock skew is the one part in 10 to the 5, so it's 10 to the minus 5. And standard deviation of the noise is 10 to the minus 5. Okay, so those are like the two numbers to have memorized when you go to design this system. Okay, so that's our standard deviation of the noise. Suppose you do 24-bit quantization. Okay, then if you look at this error, like that, how big is that? Well, you have this -1, 1 interval, so that's with length 2, right? You're dividing it into 2 to the 24 different little regions, right? Because each one is roughly like 2 over 2 to the 24 in width or length, right? Okay, so just do like rough order of magnitude here. Okay, you have 2, that's the length of this whole interval, divided by 2 to the 24, that's the number of little tiles. Okay, and I mean, order of magnitude, maybe we don't care about factors of 2, but you know the error tends to be like half the width, right? Half the width of a tile, not the full width. So you don't really need to worry about the 2. So just 1 over 2 to the 24. How do these compare? Sorry? It can be ignored. What's this? Is it power of 10? People know off the top of their heads? I can't do these in my head, so I'll show you the way I do it. So 2 to the 24, that's like 2 to the 10. That's exactly 2 to the 10 times 2 to the 10 times 2 to the 4, right? 24, right? 2 to the 10 is 1024. That's like 10 to the 3, roughly, right? Okay, so we have 1 over 10 to the 6 times 2 to the 4, that's 16, right? So you have like roughly 10 to the minus 7, right? Okay, so the quantization error is a lot lower than the standard deviation of the noise. So it's pretty safe to just lump the quantization error into the noise and assume the noise distribution is not affected too much. Okay, or you can just say quantization error is 10 to the minus 7, that's really small, so we just ignore the whole thing. Just ignore these whole blocks in the system because they don't really matter. Okay, in our case, that's reasonable. If you use 24-bit, what if you use 16? That's another possibility with the wave file, right? In fact, probably a lot of the experiments you did in labs 1 and 2 involve 16-bit quantization at the receiver. Okay, that's a difference by a factor of 2 to the 8, right? 256. Right? So take this multiplied by 256. That's about now in the order of 10 to the minus 5, right? Again, kind of ignoring the 2s and 3s and so on. Okay, so once you get to 16-bit quantization, then it's kind of on the same scale as square root of n. Okay, and in fact, like here's an experiment you can do on your own. It's not one of the official labs, but if you just send silence through the comm cloud and just make a recording of what the receiver hears, okay? If you choose 24-bit quantization on the receiver when you do the experiment, okay, the waveform you get will be something centered around 0, and it'll look like sort of a continuous waveform like that. Okay, because the quantization error, the rounding, okay, is like significantly finer than the standard deviation of the signal. If you do it with 16-bit quantization, okay, then you're going to get something more like this. Like that. Does that look familiar? Okay, I've had people in office hours come and they show me this. Is like, what is this? Okay, so I can tell you exactly what this is. This is thermal noise, okay, of standard deviation on the order 10 to the minus 5. That's quantized to 16 bits, so that the rounding error is also on the same order. So you get, noise that just kind of cycles between a relatively few values above and below 0. So it looks, of course, MATLAB interpolates it for you when you plot it, but so you get that. Okay, whether we use 16-bit, 24-bit, we're always going to lump the error into the noise. I just call it noise. Okay. The main reason is like people only have a better way of handling it. It's a nonlinear operation. So like, what can you do? In our case, you're not necessarily giving up a whole lot by doing that. I can tell you when you go to like wireless, the sampling rates tend to be a lot higher. Okay, therefore the resolution tends to be a lot lower. Okay, so you have like ADCs that are running like a much higher sampling rate, and rather than doing like 16 or 24 bits per sample, they're doing a lot less. Okay, so there it becomes even more questionable whether you can really kind of lump this into the noise, but this is what people do. That's what we'll do. So that was quantization. Any questions on quantization? So now we're here, and what's left is the finite length truncation. So this is the last step. Okay, so up to now we've been assuming in like usual, signals and systems format that all of our signals are like doubly infinite over time, either continuous time or discrete time, but they're like two-sided infinite. Okay. Okay. Of course, in real life, the encoder submits a wave file. That's a finite length vector, right? You get a wave file back, a finite length vector. Okay, so that's what I mean by finite length truncation, just the truncation in length. Okay, so let's view the input as a vector x. Say n samples. We'll call the output wave file y. Mathematically, that's just a vector y. Tell me about the length of y compared to x for ComCloud. It's longer by potentially quite a bit, right? Because the receiver starts recording first, and then after about half a second, it plays the transmitted signal, and then it continues recording for another half second afterwards, right? Okay, so y is going to be longer. So we can't index at 0 to n, or 0 to n minus 1. It's got to be longer than that. So we'll index at 0. Up to n plus L1 plus L2 minus 1. Okay, and you'll see why I write it as the sum of L1 and L2 in a moment. Okay? Okay, now the mapping from x2, the discrete time signal, to y2, the discrete time signal, is a convolution, right? We studied before what happens when you take a vector like x, like this, 0 pad it, convolve it with an impulse response, and then window it to get y, right? So we said that the output you can express as x times the Toeplitz matrix, right? Okay. This is a bit of a variation on that theme in that y is bigger than x, right? So it doesn't quite fit in that theory, that story, okay, because these things are not the same size, okay? So there's no way I can say y is equal to x times some square matrix. It doesn't dimension check, right? Okay, so there's like another, I guess you can call it a fudge. It's kind of a way around, maybe fudge is too strong. There's a simple way around this, okay, which is just to think about the ComCloud system is sort of taking your vector, padding it with zeros first, okay, and then taking that longer vector with the zero pad that to form a double infinite signal, convolve, and then window, okay? So the way I think about it is like, x, this is your input. The system is going to pad it with zeros. This is where L1 and L2 come in. So we're going to assume that it puts L1 zeros at the front, L2 zeros at the end. L1 and L2 we do not know. Okay, these are like Thieleman's random variables, I guess. Okay, so then you kind of zero pad further to get the x2 signal. You convolve with h to get y2, and then you window to get y. Okay. And from here to here, from x2 to, sorry, not from x2, but from this longer vector here to y, okay, now I have vectors of the same size. They're related just through zero padding and a convolution. Okay, so I know I can express that relation as a Toeplitz matrix multiplication. Okay, so overall you get y. This is the receive wave file, just a bunch of samples in a vector. I can write that as x, the input vector, padded with an unknown number of zeros on either side. That times a Toeplitz matrix plus z. And that's just a vector of noise samples. That's it. That's our model. I think it's remarkable that it collapses down to something so simple, right? There's a lot going on over here, right? I mean, you've got the filter. It's underdamped. It rings at 7 kilohertz, right? You've got an amplifier here, an amplifier here. There's like this sinc or raised cosine pulse reconstruction, right? You got quantization, anti-alias filtering. There's the time skew, tau, right? There's all this stuff. Okay, and somehow all that collapses down to just that. Okay, it's a Toeplitz matrix times x plus noise. Okay, remarkable, actually. This is good news for us that it collapses down to something relatively compact. So if we can just understand how to communicate over this, a system like this, how to encode bits into x, such a way you can pull them out of y afterward, right? Then we'll be in good shape to design a communication system for that whole thing, right? Okay. What is H and what is Z? So let's record here for the record. So Z is IAD Gaussian, some variance n, and it's independent of the x vector. L1 and L2 are random variables. We're not really going to specify a PMF for them because we're never really going to use it. But a Poisson PMF with kind of a large mean would be reasonable if you want to put one in. H is a Toeplitz matrix. All right, so here's a question for you. Should we think of H as known or unknown? How should we model that? At design time, when I go to design my encoder that maps bits into X, should I think of H as something that I know and my design can depend on H? Or should I think of it as something that I don't know? Something that I know? How would I derive it? How do I figure out what it is? Impulse response. Okay, so if it were unknown, then what would you do? Suppose I say we're going to treat it as unknown. We don't know what it is at design time. Then what would you do at runtime? Try to figure out H. Yeah, that's where you pass the impulse through, right? If I didn't know what H is, then like the first sample in X can just be an impulse with a bunch of zeros after it. Okay, you're going to send an impulse through the channel. The receiver can look at the response, right? And from that, learn what H is. Since it's Toeplitz, once you know the impulse response, just copy it down, all of H, right? That's if you didn't know what H was at design time, that's how you might approach it. My question is, should we assume that that's the case? Should we approach it that way, where we don't know what H is and we need to learn it at runtime? Or should we treat it as something that we know ahead of time at design time? We have to learn it. But OK, let me play devil's advocate here, right? I mean, H is just, it's complicated, sure. But H is just like derived from this impulse response here. And we had a formula for that, right? It's like homework 3, right? OK, it's the raised cosine pulse convolved with the low pass filter thing. And OK, so in principle, I mean, you can just like compute all that and write H down, right? And then we know H. We don't need to send an impulse. Would it work? It certainly doesn't sound fun, right? You think it would work?
Will it change it over time, the whole model maybe?
Sorry?
Apart from that, it's really hard to do that compared to just sending some impulse. And
Yeah, OK, so go ahead.
It might change over time, the model of those 5 blocks.
Yeah.
Maybe.
Yeah. Let me pose this question. Suppose let's not even worry about time variation, just like right at the beginning. Suppose I'm willing to go through all those calculations. Can I really figure out what H is?
Probably not exactly.
Sorry?
Probably not exactly.
Why not?
Physical things don't work.
Yeah, OK, I mean, I can write down what I think the impulse response of the low pass filter for the anti-Eocene filter, the decoder is. The reality is not quite that. But if you look closely at that model, there are things that you have no hope of ever knowing at design time, like tau. Remember tau? Tau is the offset between the samples, right? There's no way at design time you know what that's going to be, right? It could be 0. It could be, 1 over f divided by 2, I guess, right? Would be the maximum amount, right? OK, so there's stuff in there. There's no way you can hope to know that ahead of time, OK? So even if you're willing to go through all these calculations, you're never going to get like an accurate enough measure of the impulse response to be able to rely on that. So in practice, we just assume it's unknown. And you have to learn it, like by sending an impulse through. OK? So that was a lot of lead up to just saying that H we'll assume is unknown. For a similar reason, we'll assume N is unknown. N is relatively easy to learn, actually, because you got silence in the beginning, right, where nothing's being transmitted. So you can just kind of look at a trace of that and get a sense of the standard deviation of the noise, and then that's that. That's it. So that's the model in its entirety. Okay, and again, L1 and L2 are like, it's like the random number of samples. L1 is the random number of samples that the channel puts in the received signal before the transmission starts. Okay, and we don't know what that is exactly going in. Okay, so part of the decoding process is going to be to figure out how many zeros we got here so we know how many samples to delete at the beginning of Y and how many to delete from the end. Okay, so that's going to be part of the process. All right, any questions on this? Modeling in general? Yeah?
For L1 and L2, is that just like user choice, or is there some?
No, it's sort of the opposite of user choice in the sense that like, so if I send a 1 second wave file through the COM cloud system, what I get back is a 2 second wave file, right? Because the receiver like starts recording and then it waits half a second and then plays your 1 second thing and it waits an extra half second before it stops, okay? So the receive file is longer than the transmit file. And so the receive file effectively has like a bunch of silence. It still has noise, but there's no transmitted signal during the initial part. There's no transmitted signal at the end either. So the L1 and L2 capture that. Okay, so the way I think about it is like you have your wave file you want to send. Okay, like think of the COM cloud system. It doesn't quite operate this way, but think of it as sort of taking your wave file, padding it with a certain number of zeros on either end. Okay, and then playing that through and then giving you a receive vector that's exactly the length of this as opposed to the length of that. But we don't know this because we don't know exactly how many samples are going to be between the time when the receiver starts recording and the transmitter starts. We do have some course control over this, which is maybe what you're referring to. Like in the COM cloud command line, you can specify like in seconds, like how much time you want here. Do you want half a second and so on. So you can kind of roughly specify this, but you don't specify it down to the number of samples. You specify it just kind of very coarsely. Yeah. Other questions? Okay, good. So with that, done with modeling. And now we can talk about actually like communicating over these things. Okay, this is an important waypoint for us. And that from this point forward, we're just going to talk about how to build communication systems. Everything up till now was like foundation, if you will, and now we're going to build on the foundation. Not a moment too soon, right? Okay. Okay, so this is communicating over channels with noise, but no ISI. And I need to explain what ISI is. Okay, so we understand how to communicate over this channel. Okay, so how do I encode bits in X so that when all this stuff happens and you get access to Y, you can pull the bits back out? That's the name of the game. Okay, there's a lot going on here, right? I don't know what H is. I don't know what N is. I don't know what L1 is. I don't know what L2 is. There's noise. The thing's filtering. It's very busy. Okay. I don't want to consider how to communicate over the channel in its full strength right off the bat. I think it's biting off too much at once. Okay, so we're going to consider simplified forms of the model, study how to communicate over those, and then slowly add the complexity back in until by at about Halloween, okay, we'll have the full channel in play. So let's, I'll just say to simplify, to get us started, let's make some assumptions. Let's suppose H is known. Okay, so some genie appears and just tells you what H is, or the instructor just says, here's your H. Suppose H is known. Suppose N is known. Let's suppose L1 and L2 are both 0, actually. So the synchronization problem of like trying to find the transmission among this longer vector, that's also not a problem. Okay, in which case channel model's that, right? Okay, so how do we encode bits into X? All right, so just maybe let me just take suggestions off the floor. So a simple way of encoding a bit into X. Don't think about this too hard. Just blurt something out. +1, -1. That's actually too good of an idea. I wanted to. Yeah, maybe I shouldn't have. Okay, well, that's a good idea. Let me show you one idea that, in some level, is not as good as that, although it has some advantages over what you're describing. Then we'll do your idea. So first of all, before we get that, let me just mention one facet of this problem that's not included in the model because it's not really like intrinsic to the channel. But something we'll consider nonetheless. So typically, when you're designing a communication system, like you're not really allowed to just like input like any arbitrary waveform that the channel can handle. Okay, you're typically constrained in many ways. One of which is in terms of the power you can input. Okay, so we're going to assume that the X that you design, the X that encodes the bits, must have like limited power to it. Okay, and the power, you can define this power in multiple ways. We'll do it like that. Okay, so this is a capital P. Okay, so we'll assume the time average average over the realizations of X and average over time, that power is no more than P. Okay, so we'll assume we're given P. We're given an allowed power level. This is dictated by, I don't know, the FCC or by battery life considerations or the circuit designers who say that the amplifier can only amplify signals at a certain level or so on. Anyway, you're given P, okay, and the goal is to encode bits in a way that allows us to extract them afterwards and that satisfies this. Okay, so let me show you a very rudimentary way of encoding the bits, and then we'll look at more and more sophisticated ways. Let's suppose we encode 1 bit in every sample. So the bit rate is then the sampling rate, right? Like 44.1 kilobits per second, right? Let's let the U vector be our bit vector. That. And we'll assume these are Bernoulli 1/2 bits. Okay, so one approach okay, I'm going to encode a logical 1 as square root of 2p and a logical 0 as 0. That. Okay, so logical 1 gets mapped to square root of 2p volts, and 0 gets mapped to 0 volts. Okay, and you can check the expected value of xi squared. I guess I forgot the arrow here, right? This is a vector right here. Right, not that makes that big of a difference, but that's a vector right there. Okay, so expected value of xi squared. This is 1/2 times square root of 2p squared. So that's p. Right, so it satisfies the power constraint. Okay, so encoding is very easy, right? You just take, if you're going to do like a 1 second long transmission, you take 44,100 bits. Take a vector of 44,100 bits, right? Each 1 bit, map that to a sample that's square root of 2p, where p is some number that's given to us. Every 0 bit, you map it to a 0 voltage. You now have a wave file that's got 44,100 samples in it. Each sample is either 0 or square root of 2p. Send that through ComCloud. Okay? And let's suppose that ComCloud, kind of magically didn't have this L1, L2 business going on. Okay, and you knew exactly what the impulse response was, and you know exactly n. Okay, can we decode this? How easy would it be to decode this? Very easy. How would I decode it? It's like do one bit at a time. So take the 0th bit, use 0.
Is it closer to 0 or radically?
Okay. How about bit 10? How do I decode bit 10? Like this one, that's going to get mapped by the encoder. It's going to be encoded into this sample of the wave file, right? Okay, now at the receiver, I'm going to get another wave file, which is the original wave file X, filtered with noise added on top. How am I going to extract this bit from that? Can I easily? Why not? We're assuming L1 and L2 are 0. So let's put that part aside. So let's assume H is known. Let's assume L1, L2 are 0. Okay, so there's no padding issues. N is known. They're not sampling at the same time necessarily. Yeah, that's true. There's an even bigger problem though. Let's suppose they sample at the same time. Suppose tau is 0. We've still got big trouble. Okay, so you take the first bit, the bit that's index 0, right? Let's suppose it happens to be 1. Okay, so the first sample of your wave file is this, right? Okay, so now put yourself in the shoes of the, not that it has shoes, but think of yourself standing in the filter here, right? So this sample comes along. That looks like a discrete time impulse. A bunch of zeros, and then you get hit by this thing, right? What are you going to do? Sorry? Oscillate. For how long, roughly? People know? That's not a number I recommended you memorize. But if you look back at your lab 1 and 2, it depends on the sampling rate naturally, but 44.1 kilohertz, the filter will oscillate for, I don't know, maybe about 100 samples before it dies out. Okay? So you send U0 here into the channel. Okay? It's going to oscillate for about 100 samples before it's done with that. Meanwhile, what are you doing? You're now feeding in new bits, right? U1, U2, U3, U4, up to like U100, right? Okay, so by the time you send in the second bit, the one indexed 1, the channel has not finished responding to the first one yet. In fact, it's barely getting started, right? It still has like about 100 samples of go left of the impulse response before it dies down. So the trouble is the channel, if you use this kind of encoding, the trouble is the channel is smearing all the bits together, right? Each bit here influences like 100 samples at the output, and moreover, each sample at the output's got like 100 bits mixed together in it. So if you're the decoder, you can't very well just go sample by sample and threshold it. You've got to try to invert that whole mess to try to get the bits back, right? People see what I'm getting at? Yeah? Okay, that is ISI. Okay, so let's define that. Where are we here? So for our purposes, we'll say a channel for which the H is not diagonal. Has what we call intersymbol interference. Or ISI. I guess the idea being that like regular interference means like I have some other transmitter that's like blasting me with power and causing me trouble. It's interfering with me. Here it's like the individual symbols internal to the system are actually interfering with each other. So ISI. All right. How to deal with ISI is an important question. And in some sense, OFDM is the solution to that problem. Okay. But in the spirit of kind of like building this up kind of gradually and not biting off too much at once, we're going to assume away the ISI as well. Okay? So let's suppose now there is no ISI, i.e., H is diagonal. In fact, we'll assume it's just identity. Okay? So let's tally all the assumptions now. H is known. In fact, H is identity. N is known. L1 is 0. L2 is 0, right? Okay, I've just assumed away like a large number of complexities intrinsic to the model. Okay, but even with all this gone, the model is still, non-trivial. Okay, so the model is y equals x plus n. N is just a Gaussian random vector. And we have the power constraint. Okay? So when I say communicating over a channel with noise but no ISI, I mean this. Okay? There's noise, there's no ISI. Let's understand this. Okay? And once we figure this out, then we'll add the ISI in. We'll figure out how to handle the ISI. Once we do that, okay, we'll talk about the synchronization with L1 and L2. After that, we'll talk about what you do when you don't know H. After that, we're done. Okay? And you'll build a system that works over the COM cloud. Okay, so let's suppose I use this system, this encoder. Okay, I have no ISI. Now the decoding is easy, right? Because each bit passes through unmolested, right? It's not influenced by any of the other bits, right? So let's just focus on one sample I and just drop the I index. Okay, so then you just have U is Bernoulli half. X is either square root of 2p or 0. Y is x plus z. Right? Okay, what is the map decoder for this? I've got two equally likely points, and I'm observing them in the presence of additive, independent Gaussian noise. So map reduces to something quite simple.
It's greater than root 2p over 2. It's u equals 1, else it's 0.
Yeah. So the two possible transmitted signals are like this, right? Because I have two equally likely points observed in the presence of additive Gaussian noise, the map detector reduces to just the minimum distance rule. So minimum distance just involves dividing finding the midway point. That's going to be square root of p divided by 2. So to the right, we decide u is 1. To the left, we decide u equals 0. That clock has stopped and it's throwing me off. Okay. Talk about the error probability. All right, so what is the error probability of this? So we've done calculations very similar to this when we just did our map unit. So let's review. So the easiest way to compute these error probabilities is to do total probability over the u, right? So look at the chance that u is 1 times the probability of an error given u is 1. And the same thing with u equals 0. Like that. So this, I don't know if I've used this notation before. This is just like standard notation we use for probability of error. Like probability of error of our communication system, we'll usually denote that by PE. Okay? Okay, so what do we got here? These are both half, right? The error event given u is 1 is the event that y is less than square root of p over 2. And the error event given u is 0 is the chance that y is bigger than square root of p divided by 2. Right? Okay, y is x plus z given u is 0. X is 0, so this is just z. right? And given u is 1, y is square root of 2p plus z, right? Okay, z is independent of u, right? I'm going kind of fast here since we've done this calculation before in other contexts. Okay, so all you're left with, PE is 1/2 times the chance that z is less than minus square root of p over 2. That's 1/2 times the chance that z is greater than square root of p over 2. Okay, and remember the trick for converting this into Q functions? We're going to divide through by square root of n. Right? These two probabilities are actually the same because z is symmetric about 0. So I'm going to get Q of square root of p over 2n. People often write this as 1 over square root of half times the SNR. SNR is just the ratio of p over n. So p over n usually appear as kind of a pair. So in fact, they usually appear as the ratio. So we give the ratio that name, signal to noise ratio. Okay. This particular scheme, they call, not scheme, they call on-off keying. Keying is, I guess, kind of an antiquated term for signaling. Actually, it has like an on-off. The word keying has kind of an on-off connotation to it, I think. Arguably, on-off keying is kind of redundant. It's just keying, right? I'm going like this because there's this notion of keying the mic. You ever heard of this phrase? Yeah? Has anyone taken flying lessons by any chance? Like, no? Anyone into aviation? Anyone on CubeSat or? Yeah. I was in aviation as a kid, and so I used to go to airports and just listen to the air traffic control, with the aviation band radio. And so, one thing you learn as you listen is that the communication channel that they use, that the planes use and the control tower uses, is very constrained, right? Everyone's kind of listening to it and trying to communicate on it. So you need to communicate in a very efficient way. It's people talking, but the worst thing to do is to grab a channel and start rambling, okay? Because other people need to talk. So they have this whole culture about how to communicate in a very kind of succinct, efficient way. And the extreme version of this is that sometimes to acknowledge a message, if the controller says something, sometimes the pilot will actually acknowledge the message by just clicking his or her transmit button and then let go immediately, like that. Okay, don't say anything, you just click the button. Right? And what will happen is the receiver in the tower, it's squelch. This is like analog communication 101 now. It's squelch. Normally it's off, so you don't just listen to all the static, right? And then it kicks on whenever the signal goes above a certain strength. So that little click will cause the signal to go up in strength and then back down. So the squelch will turn off and then back on, and you just register the click in your ear just from that little bit of static you hear. And it's a very distinctive click. And the culture is that means yes, I heard you, I acknowledge that. It's a very quick way of just kind of acknowledging a message without actually saying anything. So it's a very, very efficient. So keying the mic. Okay, so this is on-off keying, keying the sample. Okay, so we can do better. Okay, as was suggested, we can come up with other schemes that do better. So that's on-off keying. Let me show you a different encoding. So we do the plus minus that was suggested rather than plus 0. Okay, so suppose you choose x to be plus square root of p if u is 1, minus square root of p if u is 0. Okay, the decoder. It's the same picture, it just gets moved over, right? So now the 2 points are minus square root of p and plus square root of p. And so the halfway point is 0, right? Okay, so just any positive voltage, you decide a logical 1 was sent. and any negative voltage decide u equals 0 would send. Okay? Okay, so overall end-to-end, like if you're doing a 1 second transmission, you take 44,100 bits if you're the encoder. Okay, logical 1, you map to the voltage plus square root of p. Logical 0, you map to minus square root of p. You have a wave file now where each sample is one of two values. So either plus or minus square root of p. You send it through ComCloud. Somehow ComCloud doesn't ring anymore. Okay, so the h is just identity. You get, and it's all synchronized and everything. You get a 44,100 length wave file at the receiver. For each sample, you just threshold it at 0. Positive values get mapped to logical 1. Negative values get mapped to logical 0. Okay? Error probability. Okay, so you can run through this whole thing here. The thing is, though, after you've done a number of these, you'll find that eventually you can just look at the picture and just write down in terms of Q function. Okay, you might not be there yet, but trust me, just do this calculation like a bunch of times, okay, or maybe just kind of stare at it, okay, and then eventually you'll be able to look at this and say, okay, the error probability is the chance that the noise pushes me a distance square root of p, makes a deviation of size square root of p, and the noise standard deviation is square root of n. Okay, so the error probability has got to be q of square root of p over square root of n. Okay. All right, so if you run through all that analysis there, you'll get exactly this answer. Okay, my claim is it's not too hard once you get fluent in that calculation, just stare at this picture and just write that down. And this is a useful skill to have, actually, because we'll start doing more and more complicated pictures here, and it's nice to be able to just look at it and write it down. You don't believe me? Am I saying it was obvious, actually?
I was saying, yeah, that's what I thought.
Is it? Okay. Yeah. So maybe, so try it, and then give me feedback. Because at some point, I learned to be able to do this. To be honest, I don't remember exactly when. I don't remember if I was like a Digicom student when I did this, or when I started teaching it that I could do this. But at some point, I could just look at these and just write this down. So think in terms of distance, really. It's just the error event is the chance the noise pushes you a certain distance. And it's just Q of that distance normalized by the standard deviation. It's the way to think about it. It's what that calculation is doing, basically. OK. This is called antipodal. Signaling. Signaling being kind of like a synonym for keying. I don't know why we need two words. Actually, we have more coming. Later, there's pulse amplitude modulation, and then coding. It's like all different words for the same concept. Anyway, antipodal signaling versus on-off keying. So which one's better? Antipodal, how do I see that?
Is it like easier to distinguish like a positive voltage, negative voltage?
It is arguably easier, yes. So that's a qualitative statement, right? It's easier. I'm arguing we can make a quantitative statement.
Double SNR.
We've effectively doubled the SNR, right? So for a given error probability, suppose I have a target error probability in mind, right? Okay, so here the SNR gets halved before getting applied to the Q function. There's no half, right? So if I want to achieve the same error probability here, I got to double the SNR, right? It requires twice as much power to overcome the half. Okay, so antipodal signaling, the usual people quote is 3 dB better than on-off keying. 3 dB being like a factor of 2 in dB. People seen dB? You comfortable with dB? Yeah? OK. I was talking to someone recently who said we don't cover dB anymore. So like, don't assume. OK, good. All right. OK. So yeah, it's better. The main problem with on-off keying is it's got like a DC bias to it. So it kind of wastes power because of a DC bias. One way of thinking about it. Good. I had something else to say about antipodal. I don't remember what it was. Let's run some numbers. Oh, I know what it was. You might be thinking, why do we even talk about on-off keying? Like, why is it a thing? Why don't we just go right to antipodal? Like, there's a bazillion like bad signaling schemes one can draw out, right? Why do we give this one a name and spend time on it? Okay, so that's a fair question, I think. As I've described it here, there's no apparent reason to ever use it. Like, why would you ever use on-off keying? You can use antipodal, right? And do 3 dB better, okay? So the reason I even mention it, okay, is that when H is known exactly, okay, then you never use on-off keying. You'd always use antipodal, okay? But when H is not, this is jumping ahead a little bit, okay, when H is not known exactly, then on-off keying offers certain advantages. Okay, so as a sort of contrived example, just to illustrate what I'm talking about, suppose your H, let's think of the whole thing as like a scalar problem. Suppose this was the setup. And suppose H, rather than being 1, suppose it was like plus or minus 1, like with equal probability. Okay, suppose that's my channel. Okay, so it takes X, it randomizes the sign, and then adds noise to it. Okay, if you use antipodal, then you're in trouble, right? Because you're in some sense encoding the bit in the sign, and then the channel is sort of obliterating the sign with this step right here, right? So antipodal is not a good idea here. And then if you encode the bit between 0 and something positive, right, then 0 will still be 0, and the positive thing might get mapped to a negative thing, okay, but values near 0 at the decoder you can conclude were 0 bits, and then things with positive amplitude, either net positive or negative, you can conclude was a 1 bit, okay? So this is sort of a contrived example, but later when we start communicating in the frequency domain to deal with ISI, we'll then have like complex H, and when H is not known exactly, it'll have an unknown phase, and we'll see it's almost exactly that thing. Okay, so lab 4, the first OFDM design for ComCloud, will use on-off keying. Okay, and that's why. Okay, on-off keying works well when you know what H is exactly. Okay, so that's why we talk about it. All right, let's run some numbers. So I have two, let's just use this one. This is a simpler formula. So suppose you use antipodal. With ComCloud, say P is 1. Right, our amplitude is like 1. Square root of n, 10 to the negative 5. Okay, so PE, approximately Q of square root of 10 to the minus 5. Right? That's the error probably I'm expecting on ComCloud, right? Okay, so you can plug that into MATLAB. I don't know what would happen actually. It's probably just going to say 0. My guess is. So let me show you why. So so recall the Q function. This is the tail of the standard normal, right? Okay, no one knows a closed form formula for Q. Okay, it's always written as an integral, which makes it kind of hard to do analysis because, okay, I have like 10 square root of 10 to the minus 5. Like, I got to numerically integrate this thing to get an answer, right? Okay, if I want an exact answer. Okay, but there was a theorem in the map chapter of the lecture notes that gives you an approximation for Q that is closed form. So you let Q hat of x be 1 over x square root of 2 pi, and then e to the minus x squared over 2. Okay, then if x is positive, you can show that Q of x is sandwiched between Q hat of x and 1 minus 1 over x squared of Q hat of x. Okay, this is just something from the lecture notes. I don't plan to prove this. It's just like calculus. Okay, so the point is this integral here is kind of sandwiched between two functions that do not involve integrals. They're just like closed form things. Okay? Yeah? And observe when x is big, 1 minus 1 over x squared is like 1. So qx is almost exactly q hat of x, right? So this is a rather exact approximation, accurate approximation. Okay, so let's plug this in. And we'll kind of end with this. So just order of magnitude. What kind of error probability are we talking about here? Let's see. Q of square root of 10 to the minus 5, right? No, something's not right. It should be 10 to the 5, right? I have P. Yeah, it's 1 over this, right? It's plus, I'm sorry. Plus right here, right? It's the signal to noise ratio in here, not the noise. Okay, so here, I should have caught that earlier. Here. All right, so it's just approximately, let's even drop the fraction, just do the exponent here. So e to the minus argument squared 10 to the 5 over 2. And I'm big into like order of magnitude calculations. Just drop the 2. E to the minus 10 to the 5. Are we happy with that? Is that an acceptable number of errors, you think? You good with that? Is that a pretty small number, you think? Okay, this is an extremely small number. Let me try to impress upon that. This is an extremely small number. It's like indescribably small. Like, I'm like speechless. I mean, like it's actually a pet peeve of mine when people say like words cannot describe how thankful I am. It's like, that's so overwrought, or like, why do you volunteer your own inarticulateness? Just find words. But like, I stared at this thing over breakfast this morning. It's like, how do you even describe this? So to put it in perspective, anybody know like rough estimate physicists have for the number of like atoms in the universe? 10 to the 80. Compare that to e to the 10 to the 5. This is much, much bigger than this. Much, much bigger. By a lot. Okay, not even comparable. Not even close. Not even remotely close. Okay? So you could send 1 bit through this channel for every atom in the observable universe, and you have no hope of even starting to see any errors, right? You have to do it like that thing to the power, like number of atoms in the universe, many times before you even start to see errors occurring, right? So that's what, when I say you plug this into MATLAB, you're almost certainly just going to get 0, okay? Like that's why. I don't think MATLAB can even, comprehend numbers that small, okay? So that's an acceptable number of errors, certainly, but it also sets off some red flags, right? Like this is a physical system. This is an actual communication system we're talking about. And the math says it has an error probability that low? That's preposterous, right? Can that be right? Have we done something wrong? You think there's an error in here? Did I slip an error in maybe without telling you? And it led to this almost like bogus seeming result? Looks right. But yet, everybody agrees the error probability of the true COM cloud should not be anywhere near that, right? There's no way. Okay, so the resolution of the paradox is this is not a model for the COM cloud, right? We have ignored synchronization. We have ignored uncertainty about H, right? We have ignored a few effects. We've ignored ISI. We've ignored a bunch of things, okay? So what happens is in reality, the dominant error event for a COM cloud is not that you send a +1 voltage and this thermal noise somehow ends up being strong enough to move your +1 all the way down to 0 when its standard deviation is 10 to the minus 5. Okay, that indeed has an error probability that's like astronomically small, or I guess astronomically means big, but you know what I mean, right? I mean like ridiculously small. That indeed, that would never happen. Okay, that would never happen. Okay, but there are other types of errors that can happen related to ISI, related to synchronization, related to not determining H exactly, okay, related to like interference from the power supply or outer space or some other radio in the vicinity, okay, that we're not modeling. Okay, so there are a bunch of things we're not modeling, okay, that have much, much higher error probabilities, and those are what dominate, okay? But bottom line is this is correct, okay? The chance of thermal noise is strong enough to push you from +1 volt to 0 volts. Never gonna happen. Never gonna happen, okay? All right, see you Thursday.